In my previous lecture, I talked about using the derivative of a function in order to find its extreme values, right? We could have a local maximum where the function takes a value that's larger than any of the nearby coordinates. We could have a local minimum where the function takes a value that is smaller than any of the nearby coordinates. Let's talk about more specifically, how does the derivative of a function change the way that the graph of that function looks? So if I have some function that I don't want to graph, or if I'm not able to graph for whatever reason, I can still figure out information based off of its derivatives. So let's start off talking about the derivative of f, or as we now know, the first derivative of our function, f. Here I have some curve, and it is a function because it passes the vertical line test, but I have not been given a formula for this function. We can still make some useful observations here based off the picture of the graph. For example, I see that between A and B, these 2 points here, any tangent line that I draw next to the graph is going to have a positive slope. So that's telling me that my derivative is going to be positive between A and B. And the same thing between the coordinates C and D as well. All of those tangent lines, any potential tangent line that we draw in is going to have a positive slope. So this is going to line up exactly with whether or not the function f is increasing, or if it's decreasing, then I'll see negative slopes on those tangent lines and a negative derivative. This is something that I've mentioned several times during this class, and I'm just making it explicit here. So at the very least, our derivative, f prime of x, is indicating whether the original function is increasing or if it is decreasing. So positive derivative means tangent lines have positive slope, and that means the original function is increasing. Negative derivative means that tangent lines have negative slope, and the original function is decreasing. Okay. So as an example, let's say I've got some quartic polynomial, degree 4, and we want to find where is this polynomial increasing and where is it decreasing. So I'm expecting it to sometimes be going up, sometimes be going down, and I want to know exactly when that happens. All we have to do is take the derivative of this function. So my f prime of x will be equal to 12x cubed minus 12x squared minus 24x. And that's going to factor nicely. So first of all, notice that all of these coefficients are divisible by 12. And then notice that every single power of x there is at least x to the first. So I can factor out an x, and I can factor out a 12. And then the remaining stuff left over is just a quadratic, which here has been factored for us, giving x minus 2 times x plus 1. So I actually know automatically from this factorization where that derivative is equal to 0. There are only 3 places where that can happen, and that is because I have a product here. If I have a product of real numbers equal to 0, at least one thing in that product has to be 0, whether that is the x minus 2, or the x plus 1. So if x is equal to 0, then x is equal to 0. Not a whole lot to say there. If x minus 2 is 0, then x has to be positive 2. And if x plus 1 is 0, then x has to be negative 1. So we have 3 different places where this function admits a horizontal tangent line. Okay, well, I didn't want horizontal tangents. I wanted to know where the function increases and where it decreases. So these are the only 3 coordinates where the function can switch from increasing to decreasing. A differentiable function will have a horizontal tangent line every time it switches from increasing to decreasing. That, or it might have a derivative that is undefined. Again, we're looking for these critical points. So in between negative infinity and negative 1, my function has to either be increasing that whole time or decreasing that whole time. In between negative 1 and 0, the function has to be either increasing the whole time or decreasing the whole time. And the same goes for every one of these 4 intervals. So we just have to figure out whether or not the function is positive, the derivative here, the f prime, is positive or negative on each interval. So if x is less than negative 1, I'm just going to calculate f prime of x at some point, and we'll get a negative value. And it doesn't actually matter what coordinate we choose, just as long as that x value is less than negative 1. So between minus infinity and minus 1, the derivative is negative, and that means the original function is decreasing. Between coordinate x equals negative 1 and x equals positive, or x equals 0, excuse me, the derivative is positive, and that means the original function must be increasing. Again, between 0 and positive 2, the derivative of the function is negative, and the original function must be decreasing. And between negative 2 and, or excuse me, between positive 2 and positive infinity, so unboundedly rather, f prime of x is positive, and the function must be increasing. And does this actually bear out with the graph of the function? Yes, it does. So first I have this infinite interval where the function is decreasing, and then it starts to increase for a bit. At 0, it stops doing that and it decreases instead. Then here at positive 2, it starts increasing again, and it will continue to increase for the rest of the positive x-axis.